Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is lesson 22, using sample data to compare the means of two or more populations. All right. Classwork. In previous lessons, you worked with one population. Many statistical questions involve comparing two populations. For example, on average, do boys and girls differ on quantitative reasoning? Or do students learn basic arithmetic skills better with or without a calculator? I know the answer to that. Which of two medications is more effective in treating migraine headaches? Does one type of car get better mileage per gallon of gasoline than another? Does one type of fabric decay in landfills faster than another? Do people with diabetes heal more slowly than people who do not have diabetes? In this lesson, you will begin to explore how big of a difference there needs to be in sample means. Okay, so how big of a difference in sample means in order for the difference to be considered meaningful. The next lesson will extend that understanding to making informal inferences about population differences. So here's example 1. Tamika's mathematics project is to see whether boys or girls are faster in solving Ken-Ken type puzzles. She creates a puzzle and records the following times that it took to solve the puzzle in seconds for a random sample of 10 boys from her school and a random sample of 11 girls from her school. Okay, before I begin, you may be wondering, what's a Ken-Ken puzzle? So I went to this website called kenkenpuzzle.com. And there is a Ken-Ken puzzle right here. I'm not going to go into details as to how to play, but if you want to check it out, there it is. Alrighty then. Alright, so on the same scale, draw dot plots for the boys' data and the girls' data. Comment on the amount of overlap between the two dot plots, and how are the dot plots the same and how are they different. Okay, so we're going to create two dot plots. Okay, so we are going to create a dot plot for both. So I'm going to draw a straight line here and draw a straight line here, and one is going to be boys and one is going to be girls. Okay. So there's the two dot plots. It says to do it on the same scale. Same scale. So if I look at these values, I want to see what the smallest value is in each. 39 is the biggest. No, 40 is bigger, 43. So it looks like 43 is the biggest for boys. 41, 41, 33, anything less than that, 32 is the lowest. Okay, and 47 is the highest here for girls, and for the lowest for boys it was 27. So you want to make sure you're including the lowest value and you're including the highest value. So I'm going to start my scale at 25. There's nothing below 25 in either the boys or the girls. And let's do increments of 5. So here's 30, and then 35, and you know what I'm doing, so. And where do I stop? Okay, well, how about 50? Because there's nothing higher than 47. Okay, so now we're going to plot. And so for the boys, there's a 39. I made a mistake here. Let me fix my scale. I skipped 40. Alrighty. 25, 30, 35, 40, 45, and 50. Okay. So now, boys, there was a 39, which would go just to the left of 40. There's a 38. Okay, and usually, well, I shouldn't do that there. Usually I like to put ones that are like really close, one on top of the other. No, let's keep doing it this way. Never mind that. I'm going to do them individually. 27 would be about here, just above the 25. 27, not quite halfway to 30, between 25 and 30. 36 would be here. 40 would be here. 27, there's another 27, so that's going to be second one up. 43, here's 41, 2, 3 would be a little closer to 45 than 40. 36 would be right here. Did I already have a 36? Yes, so that's going to go above this one. 34, which would be over here, and 33. Okay, so there's the boys' dot plot. Now the girls' dot plot is going to be 41. 41 again. 33, 42, 47, 38, 41, 36, 36 again, 32, and 46. Okay, so there's the girls' dot plot. All right, so now we're going to compare the two. On the same scale, we did that. Comment on the amount of overlap between the two dot plots. And then how are the dot plots the same and how are they different? Okay, so in answering that, I would say the dot plots appear to have a considerable amount of overlap. And what do they mean by overlap? Well, any data that they share. So this from here, this is the end where the girls are, and this is the end of the boys' data. So all the data that they share would be overlap. So the girls ended, well, there's two more over here, so that'd be your overlap right there. That's what they mean by overlap. Okay, the boys' data may be slightly skewed to the left because of these two dots outlying over here. Whereas the girls are relatively symmetric, so theirs is kind of bell-shaped and it's pretty even with a center around, I'd say, about 39 or 40. Alrighty. Number 2. Compare the variability in the two data sets using MAD, mean absolute deviation. Is the variable in each sample about the same? Interpret the MAD in the context of the problem. Okay, so the mean absolute deviation, or MAD, were done for us right here. So we didn't have to calculate that. So we're going to just copy this over to the next page and answer questions about it. Okay, so in comparing the MAD, mean absolute deviation, we're looking at these two values. The variability in each data set is about the same as measured by the mean absolute deviation, around 4 seconds. So for the boys, it was 4/100ths of a second above 4 seconds, and the girls was 4/100ths of a second below 4 seconds. So it's around 4 seconds. For boys and girls, a typical deviation from their respective mean times, 35 for the boys and 39 for the girls, is about 4 seconds. Okay, so the difference in the means is approximately what the MAD is. So the variability is about the same in each. Number 3, in the previous lesson you learned that a difference between two sample means is considered to be meaningful if the difference is more than what you would expect to see just based on sampling variability. The difference in the sample means of the boys' times and the girls' times is 4.1 seconds. 39.4 seconds, this number, minus the 35.3 seconds. So we're just taking the difference of the means, and it's 4.1 seconds. This difference is approximately one mean absolute deviation, 4.1, and mean absolute deviation was right around 4. A, if 4 seconds is used to approximate the values of one mean absolute deviation for both boys and for girls, what is the interval of times that are within one mean absolute deviation of the sample mean for the boys? Okay, so what we're going to do here is, So it says, what is the interval of times that are within one mean absolute deviation of the boys? So 35.3 seconds was the boys' mean. So you take that mean and you add one mean absolute deviation of 4 seconds. It's approximately 4 seconds. And that's going to equal all right, 39.3. Okay. And then we take the 35.3 and we subtract the 4 seconds and we get 31.3. Okay, so the interval of time that are within one mean absolute deviation of the boys' means is approximately 31.3 seconds and 39.3 seconds. So it's from this to this. Okay, part B says, of the 10 sample means for the boys, how many of them are within that interval? How many are between 31 and 39? Okay, 0.3. 39 is, 38 is, 27 is not, 36 is, 40 is not, 27 is too small, 43 is too large, 36 is in there, 34 is in there, and 33 is in there. So 3, 4, 5, 6 of them are in there. So of the 10 sample means for boys, how many of them are within that interval? The answer is 6. Of the 11 sample means for girls, how many of them are within the interval you calculated in part A? So now if I look at 41 is too large, 41 is too large, 33 is within, 42 is too large, 47 is too large, 38 is in there, 41 is too large, in, and too large. How many of them are within the interval I calculated in part A? So 31.3 to 39.3 is 1, 2, 3, 4, 5. So of the 11, there are 5. So before I move on, though, I'm going to calculate what I did in A for the girls using the girls' data. So let me erase all of this. And let's calculate that. So what did I do up here? I took 35.3, the mean. So I'm going to take 39.4. And I'm going to subtract the mean absolute deviation of 4. So 39.4 plus 4 is 43.4, and 39.4 minus 4 is 35.4. So how many is between 43 and 35.4? That's a 4, not a 9. It always snaps to the point on my 4. If I don't hesitate. Okay, 35.4 to 43.4. So 41 is less than 43, greater than 35. So is 41. 33 is too small. 42 is in there. 47 is too big. 38 is in there. 41 is in there. 36 is. 32 is not, and 46 is not. So that's 1, 2, 3, 4, 5, 6, 7. So I won't use this 5. I'm going to use the 7. I would not compare the girls' sample in the boys' sample. I would compare the girls in the girls. So there, the answer should be 7, calculating what we would calculate in A. D says, based on the dot plots, do you think that the difference between the two sample means is a meaningful difference? That is, are you convinced that the mean time for all girls in all school, at the school, not just this sample of girls, is different from the mean from time for all boys at the school? Explain your choices based on the dot plot. So anytime you see a question that says, do you think, they're asking for your opinion and what you think you see in a set of data that we have up here. So whenever that happens, this is going to happen. So here's a sample answer. Yours may be a little different, but here's one. I don't think that the difference is meaningful. The dot plots overlap a lot, and there is a lot of variability in the times for boys and the times for girls. Okay, so that's one possible answer. Example 4 through 7. How good are you at estimating a minute? Work in pairs. Flip a coin to determine which person in the pair will go first. One of you puts your head down and raises your hand. When your partner says start, keep your head down and your hand raised. When you think a minute is up, put your hand down. Your partner will record how much time has passed. Note that the room needs to be quiet. Switch roles, except this time you talk with your partner during the period when the person Except this time you talk with your partner during the period when the person with the head down is indicating when he or she thinks a minute is up. Note that the room will not be quiet. Okay, so 1, you do it when it's quiet. 2, you do it while someone's talking, so there's a distraction. Okay, so obviously I can't do this in the video, but I can bring in some pretend data to look at. Okay, so obviously you would need a stopwatch for this, and you can get those online, or of course these are the years of technology. Most people have a cell phone, and yeah, stopwatch on a cell phone. So anyhow, let's just say we came up with this. I'm going to just write these in. 58.1 would mean that someone was pretty close to 60 seconds. They were off by just 1.9 seconds. Okay, and I'm just going to continue filling this in. Actually, I'm just going to bring in a sample, and then we will work with that data. Okay, so this will be the data I'm going to work with in this video. And so estimates for a minute, quiet, and talking. So it says use your class data to complete the following. Number 4, calculate the mean minute time for each group, then find the difference between the quiet mean and the talking mean. Okay, so I'm just going to show you how to do it in my calculator, but I'm not going to go through the whole process. It's very tedious, and we don't need to take that time. So 58.1 is my first. So what I would do is I'd go into stat, and I'd hit enter because we're already at edit. And I want to enter my data in L1. So it'd be 58.1, enter, and then just keep going. But I'm going to pause the video to save time. Okay, so now I've entered all the data. I have 14 items in each column, ending with 64.7 and 63.8, as you can see right here. Okay, so now I'm going to go to my home screen, and I'm going to hit stat, calculate, one variable statistics, list L1 for starters, and the mean is X bar, which is 58.778, and I will just use tenths, so it's 58.8. So the mean for the quiet mean equals 58.8 seconds. Okay, and then I'm going to do the same for the mean for talking. So I'll put talking mean equals, bring my calculator back up, and now I'm going to clear, and I'm going to press stat again, and I'm going to calculate one variable statistic, so I hit enter, but now I want L2, so I'm going to hit my second button and 2 for this blue L2 here, and then enter, 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 and that mean is 64.75, which rounds to 64.8. Okay. Then it says find the difference between the quiet and the mean talking time. So then I take 64.8 minus 58.8, and I get 0 and 6. So the difference between the two is 6 seconds. 5 says on the same scale, draw dot plots of the two data distributions and discuss the similarities and differences in the two distributions. Okay, so here we go. So I'm going to choose a straight line segment, and I'm going to draw right there. That's a little thick. Let me thin it out. And let's go like right there and give it some room. Go like right there. Okay. Line them up the best I can. That looks pretty good right there. And then I want to look at the smallest amount of data. What's this, or not the smallest amount, but what's the smallest value of one of our elements in our set? 58, 56.9, 56.4, 54.7 looks like the smallest. And then the highest looks like 73.9. There's 70. Yeah, nothing higher than 73, but anything less than 54. No. Okay, so we want to now tell the reader what these lines mean. This will be quiet, and this will be talking. Distraction. Okay, so I'm going to start with my lowest value. Let's start at 54, and I'm going to go increments of 1 now just because of our data. And since it's 58.1, I'll do some rounding. Or it can go in between. That's why we want to do increments of 1, units of 1 on our scale. So 58.1 would just be to the right of 58 and so on. Okay, so I just made this scale off to the side and brought it in. So now we're just going to enter our data. So I'll do quiet in green. And 58.1 would be, let's see. Okay, so I just brought this in to make it easier to plot the dots, and then I'll just delete it after. All right, so maybe a ruler would help you if you didn't have an opportunity to do this here. So anyway, 58.1 would be right here. 56.9 would be just before 57. 60.1 right there. 56.6. Okay, you get the idea? .7, 64.5, 62.5, 58.6, 55.6, 61.7, 58 exactly. There's a dot here too. Where are we? 55.4. All right, so 55.4 and 55.6 are fairly close. So I'm going to put these one above the other. 63.8 would be here. And there was another one that was really close, right by 58, and it was 58.0, 58.0 and 58.1. So rather than having them practically touching, I'm going to move the 58 and the 58.1. So I'm going to get rid of this dot here. And let's just rotate that so I don't have to redraw them. How's that? There. All right. So there's our dot plot for quiet. All right. Now talking. I'll do it in red. All right. So 73.9 is all the way over here. 59.9, 65.8, 65.5, 64.6, 58.8, 63.3, 70.2. That's pretty bad. 62.1, 65.6. Okay. What was the other 65? 65.5 and 65.6, I'll share those. And the other one was 65.8, I think. Yes, right there. So I'll do it that way. 61.7 will be here. 63.9 is almost 64. And 66.5 or 66.6 would be here. And 64.7 would be about here. Okay, so there's our dot plot for the two. So then to compare these, I suppose I could get rid of this, and then now we can compare. Discuss similarities and differences. Okay, so the dot plots have quite a bit of overlap. They overlap from here to here. Those are all the values that they overlap. And, well, actually I could move this one to here. That would be the overlap. Okay, what they had in common. Both had dots in those ranges. So there's the overlap. So the quiet group distribution is fairly symmetric. So the quiet group, yeah, okay. And the talking group distribution is skewed somewhat to the right because of these two outliers. The variability in each is about the same. The quiet group appears to be centered around 60 seconds. So now we're talking center. Quiet group centered here. And the talking group appears to be centered around 65 seconds, which is over here. Okay, there's our that appear to be centered on our data. Okay? And that's what you would explain. Number 6, it says calculate the mean absolute deviation for each data set. Based on the mean absolute deviation, compare the variability in each sample. Is the variability about the same? Interpret the MADS in the context of the problem. Okay, so recall that what a mean absolute deviation is you take the mean and then you subtract every single value from your set of data from the mean and get a deviation. So if the mean is 58.8 seconds, for example, and the first value is 58.1, well, that's a deviation of 0.7. And then 56.9 to 58.8 is 1.2. And you'd find all those deviations and find their averages. It's a lot of work if you're doing it manually, but if you have a calculator and you entered all of your data in L1 and L2 like we have already done, okay, now I'm going to show you how to find the mean absolute deviation from those. So I'm going to go to my home screen and close it, and I'm going to press Math, and I'm going to go over to where is it? Not Math. Okay, so it's not that Math. So you have to be really savvy with your calculator. So let me show you. There's a Math button, like so. Or if I hit second stat, you see that word list there? Second stat, and you go over to Math there. Okay, and number 3 is the mean. So you can either press down 2 like this and hit enter, or just hit the 3. So I'm taking the mean of the absolute deviations. So I need an absolute value symbol, and that would be under catalog. And number 1, since it's in alphabetical order, is absolute value. So I hit enter. So I'm taking the mean of the absolute value of something. Well, what am I taking the absolute value of? The difference of every single mean, or every single x from the mean. So I'm going to take the mean of L1. So I want to take the mean of L1 minus and then we're going to subtract the absolute deviation from that, or the actual value. So we're taking the mean of L1 minus the mean of L1. Okay, so I want the average of this minus each value. So it's going to be L1 minus, and then I go back into my catalog and take the absolute value of no, not absolute value. Let me delete that. Let's see, I want that mean. So if I go back into second list over to math 3, I keep doing that. All right, so let me refresh. Let me start over. All right, let's make this clear. I want to calculate the mean absolute deviation. All right, so I hit second stat, arrow over to math. Number 3 is the mean. Number 3 is the mean. So I'm taking the mean of L1, or mean absolute deviation, mean of the absolute value of L1 minus the mean of L1. Close the parentheses for there, and a final parenthesis, and I hit enter. Okay, so I got the mean absolute deviation of the set from quiet to be 2.68. 2.67, I guess, rounding down, 2.67. So the mean absolute deviation for the quiet equaled 2.67. Now I'm going to do the same for talking. So I want the mean absolute deviation for the talkers, or for during talking. So I'm going to do the same thing again. So the mean was 64.8. So then I go back into my calculator, clear. Now remember, if I go stat enter, there's all my data already entered. Then I go to my home screen, and I want to calculate the mean absolute deviation. So it says mean. You want to take the mean of the absolute deviations. So, second catalog. I'm not going in the right order again. Second stat, which will give us this. And then we arrow over to math, and the mean is number 3. So I'm taking the mean of the absolute value. So then I go into my catalog for absolute value and put 1. So the mean of the absolute value of, now we're doing L2, minus the mean, second stat, arrow over to math 3, the mean of L2, double parentheses, to finish it, and hit enter. And I got 2.72. Okay, so there's a really quick, easy way to calculate the mean absolute deviation. Okay, so we found them, and then it says interpret the MADs in the context of the problem. Okay, so the mean absolute deviation measurements are about the same, indicating that the variability in each data set is similar. In both groups, a typical deviation of students' minutes estimates from their respective means is about 2.7 seconds, give or take 2 to 3 hundredths of a second. So number 7 says, based on your calculations, is the difference in mean times estimates meaningful? Part of your reasoning should involve the number of MADs that separate the 2 sample means. Note that if the MADs differ, use the larger one in determining how many MADs separate the 2 means. Okay, so if the MADs differ, they do, use the larger one. So I'm going to use this mean absolute deviation, 2.72. Okay? How many of those MADs separate the two sample means? Okay, so what we need to do is take this value here. The difference of our means was 6. That's what we used to calculate. So we're going to put 6 divided by the larger mean absolute deviation of 2.72. And 6 divided by 2.72 is approximately 2.2. Okay, there is a meaningful difference between the means. Okay, well, that is the end of lesson 22. Review the lesson summary and go do your problem set.